Good morning, students. And today we'll be working on machine translation with attention mechanisms, right? So in machine translation, we will be learning seek-to-seek. How do we deal with seek-to-seek kind of problem? And then in the attention, we'll be learning how we can apply what is attention mechanisms, right? I have to make sure to say that attention mechanisms is not only for seek-to-seek problem, right? Attention mechanism is a general technique that can be applied to even classification problem or even a decoding problem, right? But anyway, I think today we're going to learn a lot, right? So today, a little bit recap on the machine translation problem and the attention. So for example, we input a source text. For example, here is a German to the encoder, and then on the decoder side, we also we start sending in some start command. I mean start input, but we want to know which word is really related to this to help decode this decoding input. What we do is we after we get the hidden state of each of them, we perform a dot product or some kind of operations, right? Such that we are able to get some value called E. So, and then to normalize it, we can perform maybe a softmax, right? And that will give us the attention, right? And then, so what is this attention? This attention will tell us that, hey, maybe we should pay attention more to the first one here, which tell us that, hey, maybe this first word will be more important to decode this start, right? And then because of that, we're going to take attention, maybe this proportion, multiply with this deep, plus this, plus multiply with learning, and etc., and add them all together. We're going to get something called attention output, right? CT. And what we're going to do is perhaps concatenate this one with the original input, right? To try to decode the next word, which is could be deep, right? And then we're going to do this for the rest of them. Start, deep learning is fun, right? And then eventually we will be able to decode all the words. That is what we hope, right? So you can see that the attention mechanism is simply trying to find which one we should pay attention to, right? For decoding each specific input. As for the seek-to-seek, in a seek-to-seek problem, we're going to have an encoder and a decoder, right? And they don't share the same network, right? Encoder has it could be one LSTM, and then for the decoder, it could be another LSTM, right? So it's basically two separate network that try to talk together, right? One thing I want to point out is that the hidden states of the encoder, the last hidden state of the encoder will be the input to the as the first and hidden states to the decoder and INN, right? So that is something that you may want to take note of, right? As for the encoder INN, the initial hidden states will be basically randomly initialized, all right? So that is something we need to take a note of. So, and another thing that we have to remind of is that even though in this E, we call this energy, there are many ways to do this, right? One of the easiest way is probably basically just dot product, but you can do multiplicative attention, putting a W in the middle, or maybe even additive attention, right? In which you project H H is basically each of this, and S is basically each one of this, right? And then you can project each of them to another dimension, add them together, apply a activation function, and project them into some dimension using another vector, right? So what is the idea here? Well, there are much more. There are probably like 20 of them, right? If you look at this link, right? But the idea is by adding more parameters, you allow more flexible ways for the neural network to find patterns, right? That is basically it, right? So by adding, for example, W here and W here, you allow more flexibility for neural network to find ways to optimize, right? And of course, more parameters basically means your network is more complex. So does it mean that addictive attention is probably better? I think the answer is yes, but not always, right? In a when the translation is very simple, I'm not sure, like a very close language, then adding complexity may not be always a desire. So that is something you may want to think about. All right. So that is a very quick recap. So today we'll be having some code, and then we're going to do ETL, EDA, some pre-processing, and I already prepared some code, right? So that we don't spend too much time on um, uh, the fundamental stuff, is because we do already a lot in the previous tutorial, but we're going to focus on actually the model itself, right? Including the actual seek-to-seek, the encoder, the attention, and decoder, right? And then we're going to do some training, test on some random news, and perform, take a look at the attention, right? How does it look, right? Great. So I think we're going to start right now. And so I just import the common stuff that we use. And if you have CUDA, you can always get the device name, the torch version and the torch text version. And so I'm going to just use a dataset called multi30K, in which the source language is English. And I specify the target language to be German. All right. And then for the EDA, we can actually take a look at one sample. And sorry, you can see that the source language is a tuple of two sentences. First is the source language. The second one is the target language. And there are 29,000 sentences. So what we're going to do is we're going to split them into train set, validation set, and the test set. Okay. And the next thing we're going to do is pre-processing. So since we have since we need two tokenizer, one for English and one for German, and we also need one set of vocabs for English and one set of vocabs for German, we decide to use a dictionary, right? So we can always look up and apply that tokenizer, right? So in that case, we create two tokenizer, one for English and one for German. And this is the example of the English tokenizer. And before we actually need to build vocab, we need to create a function that can actually yield us each of the token, right? So that what do we do? Well, we just go into each of the tuple of the sentence, and then we just transform the language, right, accordingly. And then sorry, we specify the special symbols. And then finally, for each of the language, we do the vocab accordingly. So here we just put the function, and then make sure that is based on each of the language, and the mean frequency is equal to, meaning that if the frequency is less than 2, I mean, if that word only appears like once, then we don't count as a vocab. And we also have special symbols, and then we also, sorry, right, and we also specified special first equal to true, so that to make sure that we plug all this in as a initial index on the vocab list, right? And then we set the default index to be Ankh in case any word is unknown. All right. And then we're gonna just try some example right here. And then we can also bring reverse back using this. And then of course we can check the Ankh and also other special symbols. And then we can also check the unique vocabularies. All right, so that is the pre-processing, so the tokenization and numericalization. The next part we're going to do is the data loader, and it's again very straightforward, but in this time I have some kind of sequential transform function, in which it takes as a tuple. So when you see a star in the front, it means is a tuple of something. And in this sequential transform, you're going to take each of these tuple and then apply this function, all right? So the first, so this is another function that I specified, in which is a tensor transform, and basically it concatenates the start of sentence and the end of sentence together with the token IDs, and then concat them together as a tensor, right? And finally, we specify the text transform function, in which it can perform a sequential transform of first tokenization, then numericalization, and then lastly, we do a tensor transform, right? So I really like this setup, and it's very nice, and maybe you can also use it in your own code, right? Finally, we have this collate batch, in which we're going to use it in our data loader. And it's very simple, right? We just transform the text into and then just add them to the source batch. We transform target language, we add them to the target batch, and then we also have the source length, right? And then not to forget, we should make sure we path sequence, right, to the maximum length of the sentence in that batch. Otherwise, our system cannot and cannot process any samples with different length, right, in that batch. And then what we return in this collate batch is the source length, and also the target batch. All right. Finally, we create the data loaders and make sure that we turn the shuffle to false to save computation. Which because in the validation and test, we don't really need that shuffle. So here's the shape of when we run the train loader. We get a batch of source length of 24 and the batch size of 64, right? Please take note that the sequence length does not really necessary to match, because the source length of the English language is basically based on the longest sentence in the batch, and 27 here is based on the longest length of the sentence in the batch too, right? So they doesn't necessarily match, right? All right. So that concludes the data loader, right? And now we can actually start working on the model design. All right. So now we can start with this, and firstly we're gonna make sure we have the encoder. We have the decoder, and we have of course the source padding index, so that we know that what is so we need to tell the neural network always what is the padding index, right? And then finally we're gonna have the self device. So you may wonder where does this encoder and decoder comes from. It will be later on implement right here and right here, right? So we let us look at the big picture first, right? And then for the forward function, we can actually write some roadmap, right? So what we want to do is we want to, of course, initialize something, right? For to hold all this input and outputs, etc. And then what we're gonna do is send our source text into encoder, right? And then for each of the input of the target text, right? We're gonna send them to the decoder, right? And then we want to make sure that we always append the output of this decoder to a list, right? And maybe finally we return this list, right? Right. So that is the forward function we're gonna write. So let us start. So firstly we can say batch size equal to source dot shape one. All right, okay. Before anything else, make sure we know what is the shape. So this one is batch size and source length. And the target is target length and batch size. So the batch size is basically dimension one, and of definitely the target length is a target dot shape 0, and then target vocab size equal to self dot decoder dot output dim. All right, so that would be specified by the decoder output nim. And then we're also gonna make sure that we need this list, right? So we're gonna say that outputs equal to torch dot zeros and target length and batch size and target vocab size, right? Dot to self device, right? So you can see that for each of them, we'll be appending to this target, right, to the corresponding batch, and each of this output will be the probability across all the possible target vocabs. And attentions, right? We also have attentions. Will be basically torch dot zeros, target length, batch size, and then source dot shape 0 to self dot device, right? So basically, the idea of this attention is that we have all the target text, right? And it's gonna referring to the attention of each of this target word to each of the word in the source text, right? And like we're gonna have batch size number of this, all right? And then now that we initialize everything, now we can send our text into the encoder, right? And so we're gonna say encoder. So now we're gonna say self dot encoder, and we have to send in two things: source and the source line. And then we're gonna get two things back: the encoder outputs and the hidden, right? And recap that the encoder outputs refer to all hidden states, and but hidden refer to the last hidden state. Right? All right. And of course, this all hidden states has some meaning, right? If you have multiple layers, it means the last layer, right? But in this case, we're going to just use one layer, so it just means all hidden states, right? And here it's a last hidden state here. Actually, the meaning is that of each layer and of each direction. Yep. So a little bit confusing here, but in this tutorial, we're gonna just use one layer and also one direction, so you can actually imagine that this hidden is actually referring to the last hidden states. And then now we can say that the input is basically target 0. All right, so we're gonna make sure that we start with the 0. All right, and then but we have to create some mask here. Self create mask source. Yep. So what is this mask? Well, you have to recall that this source has a lot of padding, right? And so whenever we calculate attentions, of course we're gonna also have the attention for the padding, all right? For example, in the source, there are a lot of padding, right? So we're gonna have also the attention of each of this target to all this padding, right? And we want to set them to 0 because they are mostly useless, right? So in that case, we want to create mask. So if the source some of the padding is 0, then we're just gonna create a mask like something like this, right? So initially it's all non-padding, but at the end is padding. So we want to create a mask like this, right? So that we can multiply this with the attentions in later on, and make sure that we just set all this padding attention to 0, right? So we're gonna come back to the create mask a little bit, and the function is really easy to write here. So we're gonna just say mask equal to source equal to self dot source pad index. If it's equal, then it will be basically set to 1, right? And we're gonna permit 1, 0. The reason why we want to permit is that so that it's the same shape as attention. And finally, we're gonna return the mask. And since the source is basically this, the shape is this, and once we permute, it will be once we permute, we can expect that the mask is basically batch size and source line, right? And you're gonna look like this. At the beginning, it will be 0, 0, 0, right? Because it say that if it's equal to the pad index, right, then it will be 1. Otherwise, it will be 0. And whenever it's equal to padding, it will be 1, right? So that we can actually take those attention. All right, so I think this one have to be set to this one. All right, I guess it's the same. It depends on how we're gonna apply them later on. So let me make sure I understand correctly. Source equal to self dot source path index, right? So if they are if they equal, then it will be one, right? Otherwise it will be zero. Yep, I think so. All right. And then so now we once we have this input and the mass, and now we can actually say for t in range 1 and target length, we're gonna send each of them into uh, the 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 decoder. So we're gonna say self.decoder input, right? And then hidden. So this, all right. And so this hidden is basically from the encoder, right? This is the last hidden state of the encoder, and it will be used as the first hidden state to the decoder. And then we're gonna have encoder outputs, and this is basically all hidden states, and it will be used for performing attention mechanisms. And then finally, we're gonna pass the mask to, right? And this is gonna give us back the output, the hidden, and the attention. All right. So right here, take note that the output, the shape is X size, output 2. And hidden is hit them. And then we're gonna have finally the attention. And the attention is back size and source length. That is what is attention, how much attention is for this input to pay to all the text, all the source, right? Sorry. All right, and this one is basically specifically the predictions, right? All right, so now we are done. We can put this attention into place. So we're going to say output t. All right, so the output t is equal to basically this output. And then we also make sure that the attentions is equal to this attention, right? And then we're gonna we also gonna say that the next input is basically target t, right? Yes, if teacher force. Otherwise, we're gonna say top, right? So what is that? Just a very quick recap. What is teacher forcing? So teacher forcing is basically we assume that the next input is basically the next word, right? So this is referred to one, right? So this means that the next input is basically the one, right? And that is basically teacher forcing, right? We want to force the model to predict the word of the next word, right? But sometimes we don't want to always teacher forcing. We want to have some robustness and also some randomness. So we also have this top out, right? So we need to specify this. So we're gonna say teacher force is equal to random.random less than teacher forcing ratio. All right. So we just randomize a number, and so this number is between 0 and 1, and whenever is less than this ratio that we get it from the user, that we're gonna apply teacher forcing, right? Otherwise, we're just gonna say that top one, okay, top out, top one, okay, top one. Let's say top one is equal to output dot argmax 1. All right. So top one is basically basically the predictions, right? And then top one is basically auto-regressive. So you keep on predicting the next word based on the highest word, right? So by making the teacher forcing ratio to be 0.5, we hope that the model will be able to learn to sometimes predict basically the word we specify, and sometimes also use the highest probability. In that way, the model will have some diversity. Yep. And then finally, we're gonna return the outputs and the attentions. All right. So yep. So I think that is the seek to seek. A very very simple big picture what we're gonna need. But the next part is we need to code the decoder and also the encoder, right? And also the encoder. Yep. So without further ado, we're gonna just shift enter, and we're just gonna close this. The next step is the encoder. I think the encoder is actually quite easy to type, because it's quite straightforward. So we're gonna do self.embedding equal to nn.embedding, input them, and embedding them, right? So we have a module that embed the source text into embedding, and self.anon. We also have the recurrent neural network architecture. This time we're going to use GRU, but make sure that they're basically the same. Embed them, hit them, and bidirectional equal to true. Self.fc is equal to linear, hit them time 2 because it's 2 direction, and then project them into hit them. Self dropout equal to nn of dropout and dropout. All right. So for the encoder is very straightforward. We first do the embedding, and then we send it into we first pack them, right? So that it ignores the padding, and then we send to the onion, right? We unpack it, and then we get the first the -1 and -2 hidden state, and then we return the encoder outputs, right? And also the hidden, right? So that is basically what we need to do in the encoder. Very straightforward. So here is embedded equal to self.dropout, self.embedding source. All right. You may wonder like why you put dropout, sometimes no. This is just some kind of experiment, and it just once we try an error, this one just work out. Yeah. And then for the pack, we're gonna have pack embedded equal to pack. So and then dot utils dot nn dot pack, and we need to send in embedded source line to CPU, and then we're gonna say enforce sorted equal to false, right? Okay, this should be pattern sequence. Yep. Okay, that's why the autocomplete doesn't come up. And then we're gonna send it into RN, right? So we're gonna say pack outputs, comma hidden is equal to self.rn, and we're just sending the pack embedded, and we're gonna unpack them. Outputs comma equal to and details dot on dot pack sequence is a pack outputs, right? And then finally we're gonna grab the last two in, so we're gonna say torch.cat hidden minus 2. So this is probably the forward state or the backward state, either of them. And then we're gonna have -1 dimension equal to 1, and then finally we're gonna apply some FC, right? So this FC gonna make this whole thing into hit them instead of from project this hit them times 2 to hidden them, and then finally we're gonna apply activation function here, and then we call this the hidden, right? And that's it, right? And of course here I'm gonna say outputs, and yep, and finally we can actually write the shape down. Outputs is nothing but I think hidden is easier. Hidden is batch size and hit them. As for the outputs is source length, batch size, and hit them times 2. All right. Okay, great. So that is the outputs and the hidden, and we're gonna return it to the big model we have, right? And that is our encoder. So we're gonna enter that. So yep. So encoder is done. Now we're gonna implement the attention, and we're gonna use the in this time we're gonna use the additive attention, right? And we're gonna code it right now. So for the attention, we need basically this 2W and also this V, right? So we're gonna call this maybe this W. We're gonna call them maybe we're gonna call this W, and we're gonna call this U. All right, simply so that we can easily understand what we're gonna do this. And this is the mass I already mentioned, so I'm gonna skip talking about it. And then I think that's it, right? So we're gonna need 3 vectors here, V, U, and W. So the so we're gonna say self.v equal to nn.linear hit them 1 bias equal to false, right? Here we just want simply it just look like once we add them all up, right? This is gonna be in the hidden dim dimension, right? And so we just projected the hidden dim into 1, and then maybe this energy can be used as a vector, right, somewhere else. But yep, that is our plan. And I'm gonna say self dot W is so this S is basically the one decoder state, one decoder input, the hidden state, the one decoder input, right? So we're gonna say that is basically nn dot linear hit them, comma hit them, right? self.u is basically equal to, so we expect that the last hidden state here is each of them, right? This one is the each of the hidden state, right? So it should be hit them times 2 to hit them, right? So this is for encoder outputs, right? Which depicts all the hidden states, and then this one is for the decoder input, right? Great. So for the attention, what are the steps, right? Well, firstly, we have to repeat the hidden source length times. The idea is simply if you have this hidden right, which I'm talking about this, right? You have to dot product many times with this encoder outputs, right? So you have to simply repeat this hidden that many times so that you can dot product with them, and then you have to also maybe permute the encoder outputs, just so that you can perform matrix multiplication. Yep. Multiplication, and then I think and then we just oh, actually we permit one thing is sometimes we dot product, right? But for in our case we are doing addition, right? But that is the same thing, right? By permute them, we make sure that when they can be added up together, right? So you can perform multiplication or the addition, right? And then we're gonna just simply add, right? We're just gonna perform, and then we're gonna calculate. We're gonna apply some the mass, right? And finally, we're gonna return basically f dot softmax attention them equal to 1, right? So this is basically the last the step in which we normalize the attention. Yep. So we're gonna do this. So we're gonna say so firstly the hidden is nothing but batch size and hit them, and then the encoder output is equal to the source length, batch size, and hit them times 2. Yep. And we need to take note that the first hidden is basically the last hidden of the encoder, right? But eventually the next hidden will be the hidden of the decoder itself, right? So it's just so that, but this is something you have to take note of. All right, so now we can repeat the hidden source, but firstly let us capture some information. So we're going to say batch size equal to encoder outputs dot shape 1, and source length equal to encoder outputs dot shape 0. All right. So what now we need to repeat the hidden source length times. So I'm going to say hidden equal to hidden dot unsqueeze 1, and then we're gonna, so once we have 1 right here, we're gonna repeat them source length time. Yep. So now this is gonna be in this shape, right? And now we can actually perform something with the hidden and perform something with the encoder outputs, and then they can be added up, right? And because they are basically now the same shape. Yep. So now we're gonna also permute the encoder outputs a little bit. So we're gonna make sure that the batch size is in the first and the source length in the second, so that it matches to this one. But of course, for the hidden dims time 2 and the hidden dim, we need to project them using some W and U, right? So that they are in the same dimension. Right? So we're gonna say encoder outputs equal to encoder outputs dot permute 102. And now encoder outputs will be basically this, but the hit dim is 2 times 2. Yep. So that is the encoder outputs. And then now we can actually perform the attention operation. Yep. So we're gonna say energy is equal to torch.pan self.w hidden plus self.u encoder outputs. All right. And then of course we need to apply self.v here. Yep. And I think that should be it. And then we're gonna do dot squeeze 2. So so once we do the self.v, it will look like this, right? It's gonna be batch size, source line, and 1. All right. So that is what is so once after you squeeze 2, it will be batch size source line, which actually summarize the attention, right, of this input of an input across all the source text, right? So that is the idea of this energy. And of course, we need to apply the mass. So we're gonna say, okay, so let's call actually okay, so the mass is basically energy equal to energy dot mass field mass, and then we're gonna fill with a very small number. Yep. And then we're gonna that, and this is basically the attention itself, right? Great. And then I think that's it. Yep. I think this should be it. And I think we can now close this down. But I think I did not actually run this block of cell. Yep. The next thing we're gonna do is the decoder, and that this is probably the last step we're gonna do. And then once we run everything, we can run the training and test on some random news. All right. So for the decoder, it's a little bit slightly long, but it's not that long. So we're gonna do self.output dim equal to output dim, self.attention equal to attention, self.embedding equal to nn.embedding, embed them, and self.ginn is equal to nn.gru. Hit them times 2, plus the embed them. Yep. And hit them. So this is a little bit strange, right? But I think it will make a lot of sense once we do the forward function. Basically, we're gonna perform some kind of concatenation, right? And then it will make sense. Yep. Sorry. Equal to ln dot linear m times 2 plus hit them plus embed them from output. Yep. And again, once again, that you can see there's a very strange addition here. Simply we're just gonna concatenate maybe the original input maybe and the original hidden state, right, together with the energy perhaps, right. Why? Well, we by preserving the original input and also the original hidden state and the modified versions, we can make sure that the neural network can make use of all this information to predict, right? So the dropout equal to and dot dropout and dropout. All right. So that is the setup we're gonna have, and for the forward function, what we need to do, right? So firstly, we first have to embed our input, right? And then we have to calculate the attention, right? So now we already have the encoder outputs, right? So we can just simply calculate the attention, and then what we're gonna do is we're gonna now send the input to the decoder island, right? In this case, we have to concatenate. What we're gonna do is we're gonna concatenate basically the original text, right? Basically the embed, and also the weighted weighted encoder output, right? Basically the attention. Yep. And then we also once so we're gonna get some output, right? And then we're gonna concatenate. We're gonna send the output of the decoder then to FC layer, to LFC layer to predict the word, right? In that case, what we're gonna do is we're gonna concatenate the basically the output of the decoder island. We're gonna also put in the weighted and also the embed. Yep. So you may wonder like why do we need to send in this two again once, because this output is already depend on this two. Well, by keeping the original information, we can make sure that maybe the FC layer can take advantage of them and then use it to actually predict the next word. And finally, we're gonna return the prediction, right? So here is just a prediction is equal to this, basically the FC of this, right? So we're gonna return the prediction. We're gonna return the hidden. Why we need to return the hidden? Well, this will be served as the next hidden state to be sent to the decoder again, right? And then we also need to send it attention, simply so that we can use it to display the attention later on. Yep. All right. So once we decide our setup, now we can actually write our code, right? So before we actually embed our our thing. Why not we make sure we understand all this thing, right? So the input is basically one word, right, of the decoder. So it's going to be batch size. Hidden is basically the previous hidden states, and hidden dim, and it's basically source line, batch size, and hidden times 2, and the mass is basically from the seq to seq, and this is batch size source line. All right, so now we have everything. We're gonna now say embed it equal to self.dropout, self.embedding input, right? But we have to make sure that since this input is only batch size one, and so embedding won't be happy with that shape, right? So we're gonna say input equal to input on squeeze 0, right? So now we're gonna have 1 here, and the source length is basically 1, right? And then we're gonna calculate the attention. Yep. So we're gonna say A equal to self.attention hidden encoder outputs and the mass. All right. And then once we get the softmax version, so A is basically sorry, attention is basically that shape, right? So attention is that shape, and just use the bracket. What we're gonna do is we're gonna say A equal to A dot and squeeze 1, right? Simply because once we get the A, we want to multiply with this encoder outputs to get the weighted encoder outputs, and then we can concatenate them to input to the decoder. Yep. So once we unsqueeze 1, we're gonna have, yep. It's very important that we don't concatenate the attention, because the attention doesn't, it's just a number from 0 to 1, right? So you always have to dot product with A and the encoder outputs to have something meaningful for concatenation. Yep. And then we're gonna also permute encoder outputs so that it can be dot product and dot permute 102. So so in this case, encoder outputs will be it will be now looks like this. All right. So now once it's look like this, the source length will map when you do a BMM function. This will be ignored, and this will be cancel out with this, and we're gonna have basically 1 comma hidden dim times 2. Yep. So we're gonna perform a weighted operation. So we're gonna say weighted equal to torch.bmm. BMM just stand for batch matrix multiplication. And you're gonna ignore the batch size and just dot product across the batch encoder outputs. And this is gonna give us weighted and is a batch size 1 and a hit times 2. Yep. And once we have this weighted, we need to permute it back. Weighted equal to weighted permute 1102, right? And so once we permute, this is going to be in the original shape again, right? All right. And once we have that, we can now concat them into so embed is basically this. Actually, we forgot to put the shape here, right? So embedded is basically source, basically one batch size embed them, right? So we now have this embedded, right? And we're going to concatenate them with this, which is hit them times 2, right? So we have to be very careful. So this is going to be this one, right? And they will be concatenated, right? So we use this symbol to represent concatenation, and this, right? And this will be concatenated across in the second dimension, right? And then there will be embed dim plus hidden dim times 2. Yep. So let's do this. So we're going to do on an input, go to cat embedded, comma weighted. You'll see go to 2, right? And the shape is simply one batch size embed dim plus hit dim times 2. I'm sorry. And once we have that, now we can actually send them to the decoder, right? So we're going to say self.on input, comma hidden dot unsqueeze 0. We unsqueeze because that is the shape that the on need, and then we're going to get the output and the hidden. All right. And finally, what we're going to do is we're going to make sure that we send all of this to here. And notice that if you take a look, all this output hidden, they will always have this one in front, right? Here, and also even for the hidden, since in our RNN here, which is one direction, so it also will be 1, right? So what we're gonna do is we're gonna first unsqueeze them all, and then we send them to the prediction. Yep. So we're gonna say embedded equal to embedded dot squeeze 0, right? And then we're gonna do the same for hidden, and we're gonna do the same for oh, sorry. We're going to do the same for an output. And we're going to do the same for the weighted. All right. And then finally, we're going to send all of this to, so we're going to say torch.cad, embedded, output, weighted, right? And dim equal to 1. And then self.fc. And finally, this is the prediction. Yep. All right, and this is nothing but predict. So prediction is batch size and output dim. Yep. Specified by this FC. Yep. All right. Great. So I think we probably has all the code written correctly, hopefully. If not, just gonna need to fix go back. So now we have written the CQC, the encoder, the attention, and the decoder is slightly difficult, I think, in the management of the shape, but otherwise, I think it's quite straightforward. Now we can go to the training and start training. So So right here I have some weight initialization, right? And then here I launch my attention module, the encoder and the decoder, and then I plug all of them into the seek-to-seek, right? And then finally, of course, I can count the parameters, and this model is roughly 20 million parameters. And then, of course, I specify the optimizer and the criterion. And we have a very basic training function that is very similar to the previous tutorial. So I will not talk too much. One thing to talk about is this clip graph norm. Basically, it's just to prevent exploding gradients. Yep. And then we also have the evaluation part, which is again extremely simple for basically the same, right? The main thing is a torch.node grad. Yep. And finally, once we have everything set up, now we can actually run them, right? So we have this train loader length, and then calculating the time, and then this is the actual thing we're gonna run, right? But before anything else, I make sure I need to make sure that I have this folder called models, right? And then I'm gonna first train, evaluate, append all the losses, and print them out all. Yep, and I'm not gonna only print the loss. I'm gonna print the perplexity, but perplexity is simply the exponential of the train loss. Yep. So enter, and then there's some mixed mistake. So we have output t equal to output, and I think this should be outputs. This should be outputs, right? And so I think this happens in the decoder. So we're gonna go up to the decoder. All right, so let me just quickly go through. No, I think it's happening in the seek-to-seek, I guess. Yep. And so this should be outputs, right? And then let me take a look whether everything is correct. Attention, right? And all right, so that is the one part. I noticed something that I have to fix. This part. Attention up. Yep. Okay, great. So I think that should be okay. Yep. So I'm gonna just clear all the. I'm gonna close. I'm gonna close this thing. Right, and I'm just gonna run everything again, and then I let us wait for the results in here. All right, so we're gonna clear outputs, restart run all. All right, so it's training, and once again, I think this is gonna take a huge amount of time, right? So I'm gonna be back once I train everything. All right. All right, so I noticed it just take too much time for me to run, so I just quickly copy some of the results I have trained previously in my another GPU, and so you can see that once I reach 10 epochs, the loss is pretty low, and the perplexity is around 7, which is quite low, right, for translation. But of course, the state of the art is pretty very, very low nowadays, like 3, 2, I'm not sure. Yep, but pretty much lower than this, right? But anyway, I think this is our first trial, and I think we are pretty good. And this is the train loss that I have plotted, and I also load the model again, and evaluate the results. And my test perplexity is 7. Yep. All right, so now we can also, of course, test on some random news. So we can definitely first take the sample, apply text transform, and then make sure we reshape, and then we just put it into the model, right? And then we can actually monitor the results, and you can see that the translation looks quite valid, right? Also, for the attention, we notice that the attention we can also monitor. And for example, this is the source text, right? And this is the target text. We can actually use this code to plot the attention, and we can see that Zwide, right, is actually related to Young. I'm not sure that's true or not. I'm not sure how to read this, but this Weibe is related to White, right? And Mana is related to males, right? So you can see that the model is trying to detect which of the word in the source text should it pay attention whenever it's trying to decode this mana, right? So this is a very interesting attention map that you want to take a look, right? Great. So I think that sums up our video today. We're gonna maybe do a very quick 30 seconds recap, and then we can finish this tutorial. So today, what we do is we try to understand a seek-to-seek problem together with how do we apply attention mechanisms, right? And then so what we do is we load the data set of the translation. We perform some EDA. We tokenize and numericalize our data set. We prepare some data loader. We design the model, which contains a full part, right, so that you guys can easily understand. We perform some training, test on some random news, and we can also show that if we display the attention map, there's a lot of very nice information for analysis, right? So this is the part that I really want you guys to do when you're in the research papers, right? To analyze the attention and also the inner mechanisms of your neural network, not only trying to improve the accuracy, right? Yep, thank you very much. See you guys next time.